for example, let's do problems 9 and 11, just to kind of, get some practice in there. So I'm going to define all the trig functions of 2 pi over 3. And so to do this, what I recommend doing, right, is say finding, all right, I know that my reference angle is pi over 3. For anything with a pi over 3, a pi over 6, a pi over 4, we know the reference angle is just pi over that. So if you have 2 pi over 3 or 5 pi over 6 or 27 pi over 4, right, if it doesn't reduce, that pi over 4 is your reference angle. Again, that's only for these special angles that we deal with, right? It's not for weird things like 7 pi over 9 or 25 pi over 13. It's only for things where the denominator is 3, 4, or 6. So to find sine and cosine and everything for this angle, for this angle, get ourselves a new pen because this pen is dying. What we're going to do is we're going to use the reference angle in the quadrant. So 2 pi over 3 is in quadrant 2. And again, you do kind of have to know where the quadrants end, right? Quadrant 1 is from 0 to pi over 2. Quadrant 2 is pi over 2 to pi. Quadrant 3 is pi to 3 pi over 2. And quadrant 4 is 3 pi over 2 to 2 pi. So then we know the reference angle. We know the quadrant. We know in quadrant 2, sine is positive, cosine and tangent are both negative. So then we just have to figure out the values. I know that sine of pi over 3, and there's like a bunch of ways you can find sine of pi over 3. You can memorize it. You can memorize the triangle, right? For the triangle, here's my 30, 60, 90 triangle. Opposite the 30-degree angle is the side 1. Opposite the 90-degree angle is the side 2. Opposite the medium angle is the side square root of 3. We can see that sine of pi over 3 is the square root of 3 over 2. So sine of 2 pi over 3 is the positive square root of 3 over 2. Cosine of 2 pi over 3 is, cosine of pi over 3 is 1 over 2. So cosine of 2 pi over 3 is negative 1 over 2. Tangent of pi over 3 is opposite over adjacent, so that's root 3 over 1. So tangent of 2 pi over 3 is negative root 3 over 1 because it's in the second quadrant. And then we could find the other 3, right? We could find the reciprocals. And I do recommend writing them in this order and the reciprocals next to them. So I could find cosecant of 2 pi over 3 is the reciprocal of this, so that's positive 2 over root 3. Secant of 2 pi over 3 is the reciprocal of this, so that's negative 2. And cotangent of 2 pi over 3 is the reciprocal of this, which is going to be negative 1 over root 3. So you can do the work, but then you can also check your answers, right? So if we go back to the modules for a second, if I look back over here, if I look at the solutions, I can go down to number 9, like, oh yeah, here's number 9, and here's, right? And so, I mean, maybe some of them don't show quite all the work, but this shows, I think, enough work to get an idea of what's going on here. Like, oh yeah, they drew the triangle, they saw it was in the second quadrant, and then they found the values. So to very, very, very longly answer your question, Zaina, I think a good way to study for really anything, but especially math, is really to do more problems, to practice doing the things so you know what you're doing. Yeah, I do actually need to fill my water glass, so I'll be right back. Just one second. Sorry about that. No, yeah. I'm happy to answer. So do you guys have other questions about kind of the mechanics of the final or really kind of anything about the class before I just start doing math? Pens. Juice them all up. Yeah, I should re-emphasize practicing math is really the way to kind of get better at it. That, and also I should say, depending on who your teacher is for math next quarter, they might not require you to do homework, right? They might assign homework and have it not be due or not be graded. You still need to do it. So definitely next quarter, right? You need to make sure for yourself, regardless of what your professor has said, right? If they're not collecting homework, you really, really have to do it if you're going to have a chance at understanding what's happening in your class. So that is, and it's easy to say, right? You're like, yeah, I'm going to do the homework, but then you actually have to make yourself do the homework, even if it's not due. I know it's like, oh, it's not due, I don't have to do it. But if you want to have a chance of really learning the math, I know, I mean, I can stand up here and say lots of things and you can hear them, but to really kind of get it, you have to do it. So let's talk about a few things. Yeah, let's talk about evaluating trig functions. So it is important to be able to evaluate trig functions, both for the final exam I'm going to give you guys and for future classes. And there's kind of a few different categories of things that I'm going to test you on. One is your capability of evaluating trig functions that have gone around the unit circle maybe more than once. Something like, for example, cosine of, I don't know, 19 pi over 6. And so the thing about this is you have to kind of figure out what quadrant you're in. And there's numerous ways to do this. Maybe the easiest way to think about this is to first deal with how many revolutions you've gone around, because 19 pi over 6 is more than one full revolution. So if you want, you can say, well, 19 pi over 6, I could subtract off 2 pi. 19 pi over 6 minus 2 pi is 19 pi over 6 minus 12 pi over 6, which is 7 pi over 6. And now 7 pi over 6, I can figure out where we're going to be. And 7 pi over 6 is, it's more than half a revolution, right? So it's more than 1 pi. 1 pi gets me right there. 7 pi over 6, tiny bit further. Here's the thing, 7 pi over 6 and 19 pi over 6, they're not the same angle. The word we use is that they're coterminal, meaning they end at the same place on the unit circle. And all the important thing, though, is that their trig functions are the same. Meaning if you want to find cosine of 19 pi over 6, it is literally the same as finding cosine of 7 pi over 6. So then we do the usual things. We say, okay, what's the reference angle? Well, definitely the reference angle is pi over 6. Right, it's something pi over 6. The reference angle is pi over 6. And I just remember, sorry. Then the quadrant. The quadrant is quadrant 3. So I know that cosine is negative. So we know that cosine of pi over 6 is the square root of 3 over 2. So we know that cosine of 19 pi over 6 is negative square root of 3 over 2. Something I've seen a few of you do that I really want to prevent you from doing in the future is I've seen a few people write something like cosine of pi over 6 is equal to cosine of the square root of 3 over 2, which is not true. Right? When you're finding cosine of an angle, you just get the number. It's not equal to cosine of the number. So once you find cosine of an angle, you want to write that, oh yeah, it's just that cosine of the angle is equal to the value it's equal to. Or I have another one like sine of pi over 2. Sine of pi over 2 is equal to 1. It's not equal to sine of 1. They're different things. So when you're finding a trig function of an angle, once you get the value, you no longer need to write the trig function down anymore. Okay, let's look at a few more examples. Let's go with, let's find tangent of, I don't know, I'm trying to think of something interesting, of 23 pi over 3. So one thing I think a few people have struggled with angles that are more than one revolution is people have tried to subtract off kind of like the biggest whole amount of pi that they have. If that makes sense? Like, for example, I've seen people say, okay, well, 23 pi over 3, I can do the division. 23 divided by 3, 3 goes into 23 7 times. So 7 times 3 is 21, 2. And so what I've seen people do is they say, okay, 23 pi over 3 is equal to 7 pi, or 21 pi over 3, plus 2 pi over 3. And then they've said, okay, that's 7 pi plus 2 pi over 3. And here's the mistake that's happened. Is this going to, I'm going to pick a different trig function to make it matter. So tangent's kind of funky and it matters less. Let's say it was sine instead. So the problem with this is that I've seen a lot of people for this particular type of question say that the angle is the same as finding 2 pi over 3. So they said, oh, this is the same as sine of 2 pi over 3. And it's actually not. It's a different positive or negativeness. And the reason is because 7 pi isn't a full number of revolutions, right? An odd multiple of pi gets you on the left side of the unit circle. Here's what I mean, right? If you're going around the unit circle, there's 1 pi. There's 2 pi. There's 3 pi. 4 pi. Right? So every full revolution is an even multiple of pi, and every full revolution and a half is an odd multiple of pi. So there's 7 pi. And then from 7 pi, we have to go another 2/3 pi. So not all the way around, but right there. So there's our 7 pi plus 2 pi over 3. Or if you wanted, you can also think of it as 6 pi plus 2 pi over 3. So the 6 pi is 3 full revolutions. And then the remaining part is the angle that we actually have to worry about. So you do your 1, 2, 3 revolutions, and then you do your pi plus 2 pi over 3, which this part here is equal to 5 pi over 3. So the way I would probably approach this, if you're trying to kind of like think of the same angle that your angle is coterminal to, is to subtract off as many full revolutions as possible, meaning as many multiples of 2 pi as possible. So here I can see, okay, well, 23 pi over 3 Yes, when you divide them, you get 7, but 7 is an odd number, and I want the smallest even number, so I could rewrite 23 pi over 3 as, instead of 7 pi, I want 6 pi, so that's going to be 6 pi, which is 18 pi over 3. Plus 5 pi over 3. So 5 pi over 3 is the angle that we're actually kind of coterminal to. And so what I would say is that sine of 23 pi over 3 is equal to sine of 5 pi over 3. And the difference there is, right, that 2 pi over 3 ends up in quadrant 2, where sine is positive. 5 pi over 3 ends up in quadrant 4, where sine is negative. And it's negative, let's see, sine of pi over 3 is the square root of 3 over 2. So it's negative square root of 3 over 2. What I really should be saying is there's a lot of ways to kind of determine what your angle is and where it is. And you kind of have to do what works best for you. But you should definitely know an odd multiple of pi gets you over there on the left side of the unit circle. An even multiple of pi gets you a full revolution, or some number of full revolutions. What else did I write down? I wrote down myself a few other little notes there. Yeah, let's do 1 or 2 more. And I haven't finished grading the most recent homework assignment. Well, homework assignment you guys turned in on Thursday. Sorry, I know it's got busy over the weekend. But I definitely saw a few. So like there were some problems about showing that sine of 2 theta does not equal to sine of theta, and also that sine of 2 theta does equal to sine theta times cosine theta for specific values. So if you're asked to show something like this, the idea is that you want to pick an angle, right? So the question was like, show for some theta that this is not true. So we could pick something like theta equal to pi over 2. So sine of 2 times pi over 2. So this is where we have to be careful, because a lot of people actually did bring the 2 out here. When you have something like this, the idea is that you want to simplify this inside part. 2 times pi over 2 is pi. Sine of pi, well, if we're on the unit circle, sine of pi is right there. The coordinate's negative 1, 0. So sine of pi is 0. On the other hand, 2 times sine of pi over 2, sine of pi over 2 is up here at 0, 1. And sine of pi over 2 is going to be 1. So you get 2 times 1, which is 2. So these are not equal. Occasionally, you might find an angle where they end up being the same, but generally, right, for any given angle, these will not always be equal. This, on the other hand, is always equal, right? And we can pick the same angle, we can pick a different angle. You can pick, let's do 2 different angles. Let's do pi over 2, and then we'll also do pi over 6. So again, we already know what this first part is. Sine of 2 times theta. Sine of 2 times the angle we have picked is sine of pi. And sine of pi is 0. Over here, we have to do 2 times sine of pi over 2 times cosine of pi over 2. It's really, really, really important to know that this 2 cannot migrate inside the sine function. When you have a coefficient that is outside of a trig function, it has to stay outside of the trig function. It's kind of like, I always kind of make the analogy with like square roots. Like if you have 2 times the square root of 3, you can't bring that inside. Well, I mean, you can, but you can't just say it's 2, right? This is not equal to the square root of 2 times 3. You could say it was equal to the square root of 2 squared times 3, but that's not the point. The point is, right, you can't just bring constants in and out of functions without kind of thinking about what's actually happening. which means we can't, right? Not that you're like, oh, I thought about it, I did it, it's fine. You can't be like, I thought it, and now it's okay. You can only do it if it makes sense. So here it would, in this example, it would make sense if you said 2 root 3 is equal to the square root of 2 squared times 3. That would be okay. But generally, you can't just shift constants in and out of functions. Here, 2 times sine of pi over 2 times cosine of pi over 2, that's going to be 2 times sine of pi over 2 is 1, the cosine of pi over 2 is 0. And 2 times 1 times 0 is 0. So look, they're the same. It also works for pi over 3. I mean, it works for every angle because it's an identity. If something's an identity, it means it's true no matter what angle you pick. So theta is pi over, I said pi over 3, but actually I'll do pi over 6. Theta is pi over 6, sine of 2 times pi over 6. So the whole point of this, right, is not to use the formula. The whole point of this is just to use what we know and say, oh, I know that 2 times pi over 6 is 2 pi over 6, which reduces to pi over 3. And then sine of pi over 3, we know is the square root of 3 over 2. Okay, let's do it for this formula. So then we're going to say for theta equals pi over 6, we're going to have 2 times sine of pi over 6 times cosine of pi over 6. So that's going to be 2 times sine of pi over 6. Well, sine of pi over 3 is root 3 over 2. So I know that sine of pi over 6 is 1/2. And cosine of pi over 6 is root 3 over 2. And there's a couple ways you can multiply this out. You can multiply these together. So it's 2 times root 3 over 4. But then the 2, I mean, in fact, you just say it's 2 root 3 over 4. But then the 2 cancels here and here. So you get root 3 over 2. So they're the same. And this is always true. Times 11:38. I also think since we have a whole week, maybe we can give ourselves a little bit of a break. Let's go ahead and, unless you guys really have something you absolutely need to see right this minute, I think maybe we should call it an early day. Let's give ourselves 10 minutes back in our lives and take a break. I'll hang out. Oh yeah, I guess, yeah, definitely. I'll give it, yeah, you're right, and that was actually on my mind. So let me do 1 or 2 graphing examples, and then we'll call it a day. It's fair. You're a better person than I. I was like, let's take a break. But no, you're right. We should definitely, right? If there are questions to address, we should address them. So let's do a couple graphing examples. Let's do a sine and a cosine one, and then they'll probably take the last 10 minutes, to be honest. So let's graph. I should point out. So typically, I am probably most likely to ask a trig graphing question in the following way. Let's say y equal to, let's make it interesting. Let's say -3 sine of, what do I want to do? I don't know. 2, that's not exciting. Let's make it exciting. Let's make it 2x over 3 plus, I don't know, pi over 2 plus 4. Okay, so I want to point out there are 2 equivalent ways of writing a question like this. This is the way I am most likely to write it, but you probably saw in the most recent homework assignment that you guys just did, that was turned in today. You could also write something like this: -3 sine of 2/3 times, let me see. Sorry, I think that's right. Yeah, x plus 3 pi plus 4. Where the that's not quite right. Sorry. 2 pi over 4. Sorry, did the math wrong in my head. There we go. So this equation and this equation are the same. In this equation, the coefficient of x has been factored out from all the stuff that's inside the argument of the sine function to make it actually easier to see the horizontal shift. So if you're lucky and you get it written this way, which I probably won't do, but it could happen, it's automatically say, oh, our horizontal shift is 3 pi over 4 to the left. Or you could say just negative 3 pi over 4 is probably how I would think of it. But if it's written this way, which is more likely, we have to do some work. So if you have it written this way, here's the work you do to find the horizontal shift. The horizontal shift, you take the insides of your angle, which is that, right? So they're taking sine of. Also, no, so your 2x over 3 plus pi over 2, and you set it equal to 0. And then you solve for x. So one, you isolate this term. So 2x over 3 equal to negative pi over 2. And then you multiply both sides by the reciprocal of the coefficient of x. So we're going to multiply both sides by 3 halves. 3 halves times 2/3 is 1, so we're left with 1x. And here, fractions times fractions, you get a negative pi times 3, which we should write as 3 pi, divided by 2 times 2, which is 4. So either way it's written, you can find the horizontal shift. It's just that it's a little bit easier to see if it's written this way. That's not the way I usually write it. Okay, there's our horizontal shift. Let's talk about the things we don't talk about first, which is the amplitude. So the amplitude is positive 3. I know there's a negative 3 in front of the sign. We ignore the negative when we talk about amplitude, because the amplitude is just saying how much up and down there is. It doesn't matter what the sign is, but it is positive. And the vertical shift is up 4. This negative here is going to flip our graph over. So I often, when I'm writing this out, I'm like, oh yeah, that's going to give me a vertical flip. So here's what I already know. I know that my graph is going to be shifted up 4. So 1, 2, 3, 4. And then that's my new middle. And my amplitude being 3 means I'm going to go as high as 3 above that at 7, and as low as 3 below that at 1. So those are the only y values I'm really going to hit when I graph this. I'm going to have y values at 4, at 7, and at 1. And really, I'm not going to explicitly find points that are at any other y values. Yeah, so I guess we should start finding the important x values. So to do that, we have to find the period. So the period for sine or cosine, or secant or cosecant, which we're not going to graph on the final, but it's true that it's also the same. The period is always 2 pi divided by the coefficient of x. So here, the coefficient of x isn't 2, it's 2/3, right? You could write this as 2/3 of x if you wanted to. So it's 2 pi divided by 2/3, which is 2 pi times the reciprocal 3 halves. The 2's cancel, and you get 3 pi. So the period is 3 pi. So this one's going to turn out actually kind of nice, not intentionally, but that's fine. So my period's 3 pi, and 1/4 of my period is 3 pi times 1/4, which is 3 pi over 4. And it's kind of a coincidence, although not exactly, that this number and this number are kind of the same. It's actually going to make things turn out really nice. So our horizontal shift is where we start. So we're going to start at negative 3 pi over 4. And then we know that we're going to go 4/4 of a period. So when we add 1/4 of a period, we're actually going to end up right at 0, which doesn't always happen, but it does happen in this example. So our first x value is right there. Our second x value is actually going to be 0. And then they're all the same distance apart. Right? So there's 1/4 of my period. There's another quarter of my period. There's another quarter of my period. There's another quarter of my period. So before I find the numbers, just watch, right? All of these parts are 1/4 of a period. So I could actually, in fact, I'm gonna graph this thing before I actually find all those x values, even though you could probably find them pretty easily. I know that the sine function at my first important x value, where the angle is 0, right? This x value we got from solving 2x/3 plus pi/2 is equal to 0. So this first value of x is the value that makes the angle 0. And we know that sine of 0 is 0. So then when I plug it in here, I get -3 times 0 plus 4. So I start in the middle, just like sine always does. And then usually, sine would go middle, top, middle, bottom, middle. But since it's reflected vertically, it's going to flip over. Instead of going middle, top, middle, bottom, middle, it's going to go middle, bottom, middle, top, middle. It's going to go middle, and then at the next important x value, which does happen to be 0, you're going to get the bottom of the range, which is 3 below. And then at the next important x value, which we haven't found yet, you're going to go back to the middle. And at the next important x value, which we haven't found yet, you're going to go to the top. And then at the last important x value, which we haven't found yet, we're going to go back to the middle. It's going to look like this. It's going to look like your usual sine function, but flipped over. The last thing we have to do is to, and usually we probably do this before we graphed it, but is to find these x values. So fortunately, they're really straightforward to find here. Let's see, where can I write them? I can write them here. So our first x value, right, x1 is -3 pi over 4. Our second x value is 0. And again, to find each subsequent x value, you're just taking your first x value and you keep adding 1/4 of the period. So -3 pi over 4 plus 3 pi over 4 is 0. And then the next one is that one 0 plus 3 pi over 4, which is 3 pi over 4. And then the next one is the previous one, 3 pi over 4, plus the 1/4 of the period, which is 3 pi over 4. So you're going to get 6 pi over 4. And then the last one, the fifth one, is going to be the previous one, 6 pi over 4, plus another 1/4 of the period, which is 3 pi over 4, which gets me 9 pi over 4. Exactly. So this point here is 3 pi over 4. This point's 6 pi over 4. This point's 9 pi over 4. And honestly, what I usually do when I'm graphing these is I label them x1, x2, x3, x4, x5, and then somewhere down away from there, I write what they're all equal to. So I'm not crowding my x-axis with all these numbers. So it's perfectly fine if you want to label them as x1, x2, x3, x4, x5, and then write what they're equal to kind of further away, so you're not making your graph look super messy. But this is what this one will look like, and it's one full period, right? We started at -3 pi over 4, we ended at 9 pi over 4. If you subtract those from each other, 9 pi over 4 minus -3 pi over 4 is equal to +12 pi over 4, which is 3 pi, which is what our period is. So when you're graphing these, and we'll do more examples of this tomorrow because we're out of time. When we're graphing these sine and cosine functions, I'm always really thinking about breaking it up into 4 equal quarters and finding the points to graph for each of those endpoints of a quarter. And it's always for sine, right? It's middle, high, middle, low, middle, and then since it's negative sine, I got flipped over. On the other hand, if it was the same graph but cosine, right? If we were doing y equal to 3 cosine of 2x over 3 plus pi over 2 plus 4, you'd have the same x values. You'd have the same y values, except cosine starts not in the middle. Cosine starts high, and then goes middle, and then goes low, and then back to the middle, and then back to the high. That would be the cosine of the same graph, of the same thing. But the thing I'm trying to kind of impart, and I don't know, I feel like I'm circling around the words and not quite getting there, is that these 5 x values tell you where things happen. And then the vertical shift with the amplitude tells you where the highs, middles, and lows are. And then you say, like, oh, I'm cosine, I'm high, middle, low, middle, high. Oh, I'm sine, well, I'm negative sine, I'm middle, low, middle, high, middle, right? It's always the same pattern, just different.